Every Friday on the Context Engineers Discord, we bring CTOs, AI researchers, and engineers who come and present their work. This week, we're extremely fortunate to have two amazing speakers. First, Antonio Mallia. Antonio got his PhD from NYU in information retrieval. He then worked at AWS and Pinecone as a researcher and applied scientist, and he's now working on his own company, and he's going to be talking about sparse retrieval.
I wanted to chat a bit about sparse retrieval, in particular when it's applied to RAG. Because sparse retrieval, it's kind of like one of the traditional techniques that, one of the early and older way of doing information retrieval in search. Today's agenda, basically I want to cover essentially like how traditional IR relates to RAG systems. What are the advantages of sparse? What's the evolution of the traditional lexical model, which is the learned way of representing sparse vectors? And then finally, why this is not a replacement for dense. Having a learned sparse model doesn't mean you can completely go and drop your dense representation. So that's why you probably wanna have apply one of the methodology to create hybrids of the two. So, first of all, why RAG is very different from, what we were used to see in retrieval engines. So we went from, in the past years, right? Like we went from ranked list to generative evidence. So traditional IR usually sort of like focuses on ranking list optimized in fact for precision, recall, user clicks, user preference. RAG is actually going in a different direction. The retrieval, the context is actually now used, as you obviously know, by agents and LLMs and AI in general. So again, it's a very different problem. It's and probably like different techniques now need to be applied to improve specifically for context. So again, here's a pretty simple, breakdown of how RAG breaks essentially the old rule. Queries are now in natural language, very long form. They're a bit ambiguous. Before they were just keyword based, short, and so on. Optimizing now, when you optimize, you don't optimize necessarily anymore for an NDCG or map. You actually care a lot about grounding and synthesis, right? The LLM really consumes any component of the result set. It's not like a user that is going to go from top to bottom, sort of like looking at results one by one and deciding when to stop at any time, right? And then, nowadays, like, Lexical is not for the end user, as I was saying, but it's really like to fuel generation, to fuel automation. So you will probably want to be faithful and remove hallucination as much as possible, rather than yield or spawn clicks from the users. So a common stage in a retrieval system is represented by a dense retrieval, or what do we call a first stage retrieval, which is typically composed of a dense or sparse retrieval. In dense, it's the standard approach is the one where documents are represented with one or more vector embeddings. And they are indexed into like what's called a nearest neighbor index, and it's sort of like can be represented as a latent space, where each vector is essentially a point in the space, and likewise the query is also represented as a dense vector, and through retrieval mechanism that applied some either linear algebra or some graph theory, right? The most similar vectors, where similarity can be defined in very different ways, are actually retrieved and then processed by later stages in this search engine, retrieval engine. For sparse retrieval, what actually it's used is slightly different. So first of all, a vocabulary gets built. So, out of the documents of the input, a list of unique terms is built, and it's essentially representing kind of like the occurrences of terms within documents. Now, This vocabulary is basically mapped term by term to what we call a passing list. So essentially, as I was saying, like a list of references, pointers into the original document where that specific term actually appears. So as you can see, for example, the term, in this case, capital, appears in the document 3. So now you can imagine how quickly, given a query, you can very quickly select the query terms that you have identified into the vocabulary, go to the corresponding list, and then essentially where the query terms actually appear in the corpus, in which documents of the corpus they appear. So now, why is sparse retrieval interesting at all? Well, for a few reasons, actually. Memory footprint, it's actually very, very good compared to dense models. Looking at some of the experiments coming from academia, running on standard benchmarks, like a standard datasets like MS-Marco, the M25-based inverted index only occupies like 700 megabytes versus like the 26 gigabyte of a corresponding, dense model. So it's actually very efficient, at least in the basic form, to do a comparison with the dense models. Obviously, there are like quantization techniques and compression techniques that can be applied to dense vectors as well, reducing obviously this gap. But generally, like sparse is way simpler in a way to kind of get it right in an efficient way. Then latency and query throughput. It's actually some of the experiments, again, present in literature show that the simple DM25 based indexes can actually handle like pretty high queries per second, making it very, very competitive, even with respect to pretty advanced, techniques like HNSW and so on. So this shows how, sparse retrieval can also like be extremely. And then finally, there are computer requirements, which people sometimes sort of like overlook at. It's like, building an index, a dense index, means you have to embed these documents. They have to go through a transformer. They have to go through a deep learning model. Most of the time you need a GPU, if not several GPUs. For sparse, at least for the traditional way of doing sparse, that's not really needed. In particular, there's one other thing, which is dense retrieval still relies on GPU-based or anyway compute-intensive transformations that need to happen at query time. When a query comes in, you still need to transform it into an embedding. And that's an heavy and expensive computation. Is sparse a replacement for dense? Not really, because we've seen that sparse really captures like lexical overlap, can be very, very precise with names and entities, can be very interpretable, you know exactly what you're matching. It's very efficient. Is that all? No. Because dense retrieval actually captures semantic similarity, which is, again, extremely important today, in particular when it comes to RAG. Because in RAG, you express, again, in your prompt or your query natural language, and it's really hard to make sure that your vocabulary is aligned with the documents, the person or the LLM or the input may come from a different distribution in terms of like terms and vocabulary. So again, dense retrieval capturing like semantic similarity, doing this fuzzy matching is able to generalize pretty well. Combining them, it's definitely like one of the right way of tackling, creating an hybrid. So how do you combine dense and sparse? Well, there are different techniques. Those are called usually fusion techniques, or they can be rank fusion or score fusion techniques. The idea is basically to run dense and sparse retrieval as separate components, come up with two different lists, two or more different ranked list of results, and then combine it either by summing their row score, summing their normalized score, doing an alternating merge. So, college with the other one, or rank based on, or fuse based on the ranking. Some other people also propose to kind of like do retrieval with one technique, for example, sparse, and then re-rank the results with the dense representation, or the opposite. Those are always very interesting. There is a lot of like debate about like which one is better. It really depends, and I think it's a very heuristic approach. Anyway, it's definitely pretty clear also in academia, but like in general, we know by running experiments that they have dense and sparse have sort of like, as I said, complementary objectives. One nice thing that has been tried is really how to highlight and enhance a bit more like these complementary objectives by saying when one of the two is failing at retrieving the right document, actually push harder on the other one to retrieve it, because maybe like it has certain characteristics, like that specific training example has specific characteristics for which the other model is actually better suited for. It's a better candidate for this specific example. And so the idea would be that while training like these two models, you train them simultaneously, and if one of the two fails that specific training example, then you try to push hard on the other one and make sure that the other one actually learns it. What people use today versus what is available is probably just the tip of the iceberg, in the sense that, when we think about lexical retrieval, in particular sparse, people think just about BM25. And I think that's also one of the reasons why sparse probably didn't take off as dense retrieval models. Because obviously the BM25, it's they get old method. It's definitely fast and solid, don't get me wrong, but like it doesn't really reflect recent progress, the transformer era, and the recent advantages we got with this model. I think and people think in general like that sparse deserves sort of like a second chance. And in fact, the history of learned sparse models. So these sparse models don't rely just on the statistics of BM25. So the traditional way of doing lexical or sparse retrieval. These learned models actually have had an evolution since 2019, essentially when transformers came out, up to today, where there was a huge amount of research done in these past 6 years. And you can see how old BM25 initial proposal is compared to today. But like looking at the gap, these 25-year-old gap, it's basically telling us that BM25 actually was and is still like a very solid method that has worked well for so many years. So speaking of a learned sparse model, let's briefly look at what those are. Let's try to understand a bit more. So the idea would be that a query and a document, instead of just relying on some statistical model, computational statistics within the corpus, etc., they actually enter a new dimension where they also use deep learning, essentially like transformers, to generate scores. So again, it's an end-to-end trainable model now. We know that the memory footprint is way smaller than the dense models. The term importance is really tailored to the task now. And it's also like, it gives you like the ability to do some better understanding of your queries and their documents, in particular, given the context within these terms, with the efficiency that you get from sparse. And I'm going to tell you a bit more about what I mean when I say learn within the context of the documents. So first of all, let me give you an example of how like learned sparse model is, how this composed, what's the architecture. So essentially a document is really like a set of terms with tokens. And these tokens enter like what's a contextualized language model encoder. So a standard transformer encoder only, you can think about it as BERT. The output of that is literally one dense embedding per token. This is exactly what a dense model is also doing. It's producing one embedding for every token. Usually dense models have an additional head on top, which will either compute the average of these vectors. So some form of like aggregation, just to make sure that all the vectors produced will sort of like collapse into one, which is going to be representative of the document. Learned sparse models take a different path. They use an impact score encoder, which is nothing else than a simple multi-layer perceptron, essentially, that will project the embeddings into a single floating point score. So you can look at this as the generative vector of a single value. And so now you have an association between a mapping between a token, an input token, and a score, and a weight, if you wish. So when you get a query and you want to compute the similarity between the query and the document, the first thing is trying to understand what query terms will match into the document. And so where the lexical equality actually happens. So if in this case, for example, Q4, the query term number 4 is equal to the term 1 in the document, that's considered a lexical match. Now, this lexical match means that you're going to take the corresponding score S1 that was produced by the model, and that will contribute to the final query to document similarity score. So the query to document similarity score is nothing else than just the sum of all the matching query terms with document terms, looking at their corresponding score. And how do you train this model? Pretty standard pipeline. I mean, the same way you train the dense models. It's in this specific case, looking, for example, the training samples from MS Marco, right? You have knowledge and labels around how a document with respect to a query. So you can create like these either pairs or triple or tuples of relevant versus non-relevant documents. And you can compute these two similarity scores, apply an optimization, and back propagate back to the model. Just to look at some of the numbers, this is like on the left hand side we have the track. This is something that runs every year, and you have the blue bar, which is DeepImpact. Green one, it's BM25. On the right hand side, you have the beer data set, sort of like out of context in a way, not trained on any of these models, and you can see that DeepImpact generalizes pretty well. The zero-shot experiment. So why is the context so important? Easy. Because if you have two words that have very different meaning, in the first example, we have the word those that means the deer, females of the deer family, right? It's a mammal, but it's written and spelled in the same way as the verb, right? BM25, because of like the way it computes scores, will assign the same score. Although they have a very, very different meaning. In particular, in the second case, it's an auxiliary verb. It doesn't really matter that much, and it's still getting the same score as the first example. On the other hand, if you rely on the context, if you rely on the contextualized transformer, you are able to understand that the first occurrence is way more important than the second one. And so DeepImpact in this case, but any learned model really, is able to assign pretty high impact score, making matching way different and ranking way more accurate. So finally, why DeepImpact? What's the difference between this and the few other learned sparse models? Well, essentially, like DeepImpact creates this association between what I call whole word tokens. So tokens that are not really limited to the BERT vocabulary or the transformer vocabulary. Because, for example, in BERT, you're really limited in the number of tokens that you can represent. DeepImpact with some techniques essentially like reconstructs the original word. So in this case, for example, for the sentence that you can see, mitral is actually maintained as a single word. Instead, the other standard like learned sparse models most of the time will split it into MIT RAL, which has two different words, and this will mess up a bit, sort of like the lexical matching functionality. So finally, if you do a comparison between learned sparse model and a dense model, you can see that in terms of like retrieval quality, for some queries, one is better than the other one, and sometimes it's the opposite. The reason is for every query, there is their sort of like way of ranking and matching. Does it mean you need to pick one for every query? Not really. Again, there are fusion techniques that allow you to combine these two result sets. And as you can see, the yellow curve is always better than the two other ones, which represent the two single models, right? And if you combine it, your recall is slightly better than taking a single model. Finally, there is a new model that came out, which I like because it also takes into consideration entities. Entities are particularly important, and being able to match entities, names, cities, organizations, it's obviously super valuable. And being able to assign a score to an entity can be done, with a learned model. So finally, I think the RAG space is is getting very interesting for several reasons. So the kind of like techniques that come out are constantly new and exciting, and you can see how it's a very fast moving space. I think there's been a little bit of hesitation on learned sparse models. I would really recommend having a look at these models, trying them out, and integrate it into your pipeline. In particular, if you are operating in certain specific verticals for which a lexical match is extremely important. Thank you, everybody.